Welcome. We are going to do a senior design presentation today. This is a team that started in January and then took a little time off over the summer, and they're coming back at the beginning of this semester to sort of let you know where they are and what their plans might be, what they've already accomplished and what they'll try to accomplish in the rest of the semester. So I'll let them actually introduce themselves.
Good afternoon, everyone. We are Team Sniff. My name is Robbie, and I'm joined by my wonderful teammates, Ashley and Lalo. And yeah, we're going to be giving our presentation today, our second quarterly presentation. So here's an overview of kind of what we're going to go over, just the introduction and background of what our problem is and what we're trying to solve, our project objective, the design, or our progress we've made in our design, what we want our final design to be, and looking forward, what we have left to do, and just kind of recap it all at the end. So our background and our problem is basically food waste. So the USDA approximates approximately 30 to 40% of the food supply in America is wasted, and a lot of this is household waste. So we're trying to eliminate the fact that a lot of people throw away their food through throwing their stuff away past the sell-by or best-by dates. A lot of these dates can be ambiguous. They're not really regulated by any particular body. It's just something the manufacturer will put on there to kind of, protect themselves. So a lot of food stays good past these sell-by dates, and a lot of people don't know that. So it results in a lot of food waste. And we wanted to focus on chicken because it has most recently become the most consumed meat in America. The average American will eat about 90 pounds of chicken a year.
How many chickens is that? Oh, I'm just kidding.
So I'm not quite sure how many chickens that is. It's a lot. So our solution is to create a device that can basically tell consumers whether their chicken has spoiled or not. And this spoilage, since it's caused by bacterial growth on the chicken, and that those bacteria emit volatile gases, we're trying to track the hydrogen sulfide gas that's emitted from these bacteria. And basically, through the proportion of the concentration of hydrogen sulfide gas, we can tell whether the chicken has spoiled or not. So we took a little bit of preliminary data last semester. There's already a product out on the market called the Food Sniffer that kind of does this. It's pictured here on the slide. So we purchased one of these and used it to kind of get a gauge on, how much time really is it past the sell-by date before you can refrigerate chicken and what kind of their scope was. So we bought some chicken tenders, which the sell-by date was the 20th of March, and we tested it all throughout the next week. And somewhere between the 25th and the 27th, the chicken had spoiled through both the sensor reading and from what we could smell. So that's kind of our goal for our sensor, is to try and gauge it around a week and see where it goes. So I'll hand it off to Ashley for this next portion.
So yes, so our project objective was basically to design a device that would accurately detect when spoilage was happening and when it had reached an undesirable threshold. Our 3, 4, 5 kind of things that we wanted our product to be was safe to use, obviously, reliable and accurate, especially when it comes to something that you're going to be eating. You want it to be reliable, and then easy to use and easy to interpret by the user. So we kind of came up with 3 alternative approaches: a refrigerated container, a tabletop chamber, and then our no contact probe. So for the refrigerated container, it was kind of modeled after being really similar to like household Tupperware. And the lid would contain the sensor, it would be built in. And then we would use like LED indicators instead of, the Food Sniffer uses like Bluetooth. We thought we'd just kind of make it simple and do LEDs. The sensor would be taking continuous measurements and still displaying LED lights. And then one of the things that we were kind of worried about with this design is humidity and temperature. So when you keep things in containers in the fridge, humidity tends to build up, and then the colder temperatures in the refrigerator we were worried about them damaging the sensor. So for the next design, we had a tabletop chamber. We kind of imagined this being like size and usage similar to a microwave. Maybe not as large as a microwave, but still having the interface in the front, opening a door, putting something in. The chamber would contain the sensor on the inside. LED lights would be on the outside of the chamber. One of the things that we were worried about is this being a little bit larger than our other designs, and it might also be a little bit more difficult to clean, maintain. You'd have to make sure that you were sanitizing it every time that you would put something in and take it out. And then because we're measuring buildup of hydrogen sulfide gas, it might be a little bit time sensitive. You'd have to put it in there, leave it in there for a little while. And last but not least, we have the no contact probe, which would be very similar to what's already on the market, the food sniffer. It's basically this very handheld sensor would be at the end of the probe, LED lights on the handle of the probe, and then one of the things we were worried about is the same kind of thing, the escape of gas. When we used the food sniffer the first time, there were 2 different ways to measure. You could do like sticking it on, keeping the lid on something, or just taking the lid off and measuring the chicken. And we kind of found that those different methods gave us different results. So we were a little worried about the escape of the gas if we used a contact or no contact probe. And then we wanted to do something that was a little bit different than already on the market.
Okay, so I'm going to talk about how we came up with the final decision. So I actually kind of already talked about the advantages and disadvantages of our previous design, so I won't go back over that. But basically we just sat down as a group and thought about safe, reliable, accurate, those 3 keywords we talked about earlier, and kind of how we wanted, like what we wanted each category to cover. So on the far left are the big categories we wanted to cover: safety, cleaning, the aesthetics of the design, accuracy, how easy it was to use, and the price of the design. And then at the top are the 3 designs. Now 1 to 5 was a scale we used where 1 was the worst, 5 was the best. And then we weighted each of our categories for a total of 100%. Now obviously accuracy we weighted the most because at the end of the day that's going to lead to less food spoilage, less sickness in people. So we thought that should be the most important factor. And then the price, because chicken is so widely eaten, we wanted it to be in as many hands as possible. So and cheap price is also really, really important. And then finally, safety, cleaning, and then ease of use. We kind of thought those were similar weights. Now when we talk about safety, we're not really talking about whether you get sick or not. It's about, does the device cause any harm to you? And they're all relatively safe devices. Maybe the tabletop container is a little bit too heavy, but all relatively safe. And then lastly, aesthetics was weighted the least. As long as the device works, aesthetics comes a little bit later. So that's kind of how we gauged our the categories of our design. So our final design, we took sort of the idea of the probe and the refrigerated container and combined them together. So the container will sit in the refrigerator with the chicken, stopping the chicken from going bad. And then when the user wants to take a measurement, they can attach the sensor to the top of the container. So that limits the humidity concerns. It's reading the temperature at room temperature. That limits the temperature concerns. A colored LED light will be on the sensor, red, yellow, and green. Green will mean that the chicken is still safe to eat. Red, obviously, meaning that it's bad to eat.
Okay, so yeah, so this is basically just a compilation of all the materials that we're thinking we're going to need at this point. The reason that we split it up between the initial cost and the cost per unit was a lot of these things can't be bought individually. So startup cost, obviously you'd have to buy packs of things and that kind of stuff. So we wanted to break it down a little bit more. But we're going to need a sensor, obviously. A microprocessor will be used to program the sensor and make the data that it's collecting something interpretable. The body we're actually planning on 3D printing, and so that will basically just be a housing to contain the wires, the microprocessor, the sensor, and all that stuff. The LEDs we'll need for display, the battery connectors, jumper wires, and then we thought that we would just kind of do it quick and dirty and buy a Rubbermaid container instead of going as far as making our own container.
So the sensor we're going to be using is the MQ136 hydrogen sulfide sensor. It's an analog sensor. We figured we could convert that signal to digital so that we could have our LED light display accurately. The important thing about this sensor is it's exclusively for hydrogen sulfide. One of the problems with these sensors is, like, if you get a broad sensor, there's a lot of gases given off by these microbes. So a lot of the times these readings, the readings can be inconclusive or not as accurate if you're reading too many gases. So we wanted to focus on one specific gas to make the reading as accurate as possible. So we made a calibration curve of our sensor. At the bottom is hydrogen sulfide in parts per million. And then on the right there is a ratio of the resistance of hydrogen sulfide that the sensor reads in the gas over an initial resistance of just hydrogen sulfide in the airspace. Now when you read the sensitivity graph on the data sheet, it's on a logarithmic scale, but we plotted it in Excel, and the line is pretty linear, so we just decided to go with a quick linear line, and that's going to make the calculation simple and make the processing it's going to make the computer not have to process as much information.
So looking forward into the upcoming semester, I'm pretty sure are ordering our sensor within this week. So ordering the sensor and then testing it and calibrating it properly. Of course, all sensors are going to be a little bit different. That was just our general calibration curve. We still need to account for potential temperature, humidity differences, and make sure it still lines up properly. As well as programming our microprocessor. So essentially putting the sensor will turn into a change in resistance. So just using Ohm's law to say, hey, at this voltage, because we'll have the red LED light displayed or the green and so on. And then creating our official design drawings through either Inventor or AutoCAD, as well as our circuit drawing and diagram. And then from those, building the sensor housing and hopefully being able to 3D print that. We're hoping to use the new Innovation Center on campus. I know they have a bunch of 3D printers there. And then it was priced at I think like 6 cents a gram, which is how we got our cost for that before, for the housing. But here is our Gantt chart for the remainder of the semester. I didn't want to put the whole thing on there because it was so large, so I just included it from the start of the semester to the end of the semester. Basically just includes building this report, ordering all the parts, building the first prototype, doing our data collection for that, refining the prototype, continuing our data collection analysis, and then putting it all together in our final report. And last, this is our linear responsibility chart, just breaking up how we wanted to do all the individual tasks. It's more broken up in the beginning, but all the final stuff is more of a group process, just going in and testing and analyzing the data. Here are our references, and are there any questions?